There's a deck of cards. You can see we have hearts, diamonds, spades, and clubs. You'll see it goes from ace to king and so forth. So we can refer to that. Suppose we draw a card from a deck. We pick a card, right, showing that drawing a heart and drawing a king are independent events. Well, the probability of drawing a heart, right? There's 13 hearts over here out of 52 is 0.25. Now, if they're independent events, then the probability of drawing a heart given, right? Given we picked a king, I'm going to adjust that probability. It's not 13 out of 52. The probability of picking a heart, given we know that the card is a king, would be 1 out of 4. We think about that real quick, because when we look at the cards, if we know the card's a king, there are 4 kings, but there's only 1 heart, king of hearts. So hence that gives us what we call the 1 out of 4. And then 1 out of 4 is 0.25. Now, because those two probabilities are equal to each other, we then say these events are independent. The probability of picking a king is independent of the probability of picking a heart, because those two values are equal. Now here's a little bit more in-depth example, kind of in the medical field. I filled in this table, right, given some information. So we have this table of values. So you'll see here. So we're looking at the different labels, right, that appear on the medicine that doctors and nurses administer the dosages, right? So you either have what's done in a concentration way, which is shown up here as an example, right? Or they give it as a ratio, 1 milliliter out of, right, as a ratio. So does that affect if they give the correct dosages, the wrong dosages? So here is what we call a contingency table. So what's the probability that a doctor gives a correct dosage, right? In this case, it's 13 correct out of total 28 outcomes, right? Look at all the different, with 11, 2, 3, 12. These numbers come, they were missing on our note sheets, but those numbers go there from the example from our online homework. So that's where you get the probability of being correct is 13 out of 28. Now, what's the probability of being correct given that we're looking at a ratio label? So in this case, what's the number, right? How many outcomes do we have that are correct in a ratio label? That's 2. Now, how many outcomes are related to a ratio label? And that's 14, 2 plus 12. And so that's where you get the 2 out of 14 from. So is the probability of getting correct equal to the probability of getting correct given we know we're looking at a ratio label? These are two different values, which means they're not independent. Somehow there's a relationship between the type of label there is and whether you get a correct dosage, which in reality could be a scary thing in the real world, that depending upon what's on the label, you could get a wrong or correct dosage. They're not independent events. They are related in some way. And that's an example of an application of this idea. Now, again, we talked about conditional probability earlier, right? And it's the probability where we consider another event has occurred prior, and we have this this notation. So I want to reinforce it again as we do that. Now, the class challenge, I'll let you try that. You have that page. Go ahead and try that, right? But here are the answers to check your work. Probability female, probability of piercing. So take a look at how we got these calculations, right? As we do that, I'm not going to read through it. You have the answers, and go ahead and check those to see that you, as a good practice problem, to see if you can get the same answers. And notice, before I say goodbye on this, I'm using the counting method. I'm just counting all the different possible outcomes based off of what events we're looking for, right? Probability of being pierced given you're male, probability of male given that you were pierced, or male and being pierced independent. So you're then going to calculate these things and check. Turns out they are dependent, being male and being and piercing.